Right? Yeah, and my name is Alexey Skrov, and I'm a data engineer at City of Bern, so I'm not really a data scientist, unlike most of you here. So please be kind. But that's my third presentation at this meetup, and that's amazing learning opportunity. So I suggest anybody who wants to learn more about data science to come here, talk to Bruce, talk to Matt, and present, because that's the best way to learn. And every time I give that kind of presentation, I usually learn a lot, and you're exposed to something that you would never actually do like on your own. And yeah, that's my experience, and I suggest you to do the same. So the challenge that I was working on is called What's Cooking? And the reason I took that challenge and decided to do that actually before it was completed, so I didn't know what kind of solution I will be presenting. The reason is that I have a side project which I do in spare time, and it's somewhat related to food, although I'm not a cook, for all of you political junkies here, if you know what it means. So my side project, that's a shameless plug. That's a mobile app that you can use in a restaurant to scan a menu. So you basically point that application at the menu, and through the camera you can see like additional information that is not available in the menu, like nutritional values, maybe some images, and maybe some reviews if somebody already left the review. Unlikely it will happen now because it's just in beta. It was just released maybe like a couple of weeks ago. So, but that's just some project that I have fun with in my spare time. So just to apply some machine learning in real life. And let's talk about the challenge. The challenge is very, very straightforward. So the goal is to recognize or classify the cuisine based on ingredients. So you have a number of ingredients, and you just need to tell for this recipe where it's coming from, which country it's coming from. So there are like, I think 17 broad categories, like Russian, Italian, Spanish, US, Mexican, and so on. So basically, you just need to decide which country this recipe is coming from. And the data is provided in JSON files, and it's like very, very straightforward. So you have a number of ingredients, and you have a cuisine. So for example, you can look at that, and in most cases, I think most of us would be able to differentiate, right? So if we can differentiate, probably there is machine learning algorithm that can do the same. So if you look at this recipe, for example, you see that there is masala, there is some kind of turmeric. So it's like very likely that's Indian. But because that's a training data, we know for sure that this is Indian, right? And then let's say for Greek, what do you expect? Olive oil, feta cheese, and so on. If you look at the test data, it has exactly the same information, but obviously missing our target here. So we don't know which cuisine. And again, like if you look at that, you probably can guess some of these. Like first one, probably Jamaican. Second, I'm pretty sure that this is southern US. And third one, who knows? So obviously there are some recipes, and some of them are really, really small ones. It's like basically water and flour. Like something like you would never be able to tell it. You basically know this is bread, but is it like Mexican bread or Italian bread, you wouldn't know.
Do you know who sponsored this competition? Like, this must have taken a lot of work.
Yoomli. Yoomli is a pretty good website with the recipes. A nice mobile app as well, so you can kind of find any kind of recipe. Good blog as well, so they have lots of data. Okay. I think we have like 300,000.
300,000. Okay, that was my question.
That was going to be my question too. Okay, that was also my question.
Maybe I was wrong. So how many? It's like 8,000 maximum for Italian, so it's probably 30,000. But they have much more data in there, right? So all of these, you can see actually all of the targets there, like cuisine. I think it's 17. I believe it's 17. And then the number of ingredients, you can see the distribution everywhere from basically 2, I think 2 is the minimal, and all the way to like 40. And as I said, like, even if you're really good in terms of like recognizing different types of food, I don't think you would be able to recognize 100%, not even 90. So we will see how the algorithm did that. But I think that's probably close to the limit. Like, obviously, like if you have like 2 ingredients or 3 ingredients, there are like hundreds of them, like having just 3 ingredients. No way.
So there's no data on the amount of each ingredient, like how many onions or how much? Okay.
No, just the number. Oh, sorry, just the name, not the number. Kenneth?
Yeah, is it multi-class competition, or you label in only one class?
That will be one class.
And in terms of like data quality, are you seeing things that are like bleached flour versus all the different other kinds of flour?
Actually, it's not ideal. It's not bad. Because obviously, like on my side project, I've been doing some of the cleaning, and usually it's terrible. So this one wasn't really bad. But there were some people actually did the whole competition without cleaning data, and they did pretty good. So, but to get to the top, you had to do some kind of like additional cleaning.
Hi, there are 6,000 unique ingredients, but only about 3,000 words.
Do you have the case or examples that different dishes may have the same set of ingredients?
Absolutely. Right.
Do you have that case in this data?
You don't know. Right, this is just a cuisine, so. Oh, like you mean the example? No, the example, every example would be unique, but.
I mean, maybe different dishes, but the ingredients are the same?
I don't think so.
You know, okay,
no.
Yeah.
I haven't met any mention of this. I didn't come across any of this. So, as I said, these can be like for some of the recipes, it's like very straightforward. You can see something that is like 100% only Indians use, or like Jamaican or whatever. But for some of them, it's actually pretty hard. So there are, it's just 2 pie charts I took to show you the distribution of all different, and this is top ingredients for these 2 cuisine. And excuse me. Basically, you can see that the combination is pretty close. And there is another one, I think a better picture that would show you how close it could be for some of the cuisines. I really like first one, it basically shows the correlation between different cuisines. And you can see that there are two big patches here, which are very close. And for example, Thai, Vietnamese, Japanese, Korean, Chinese, they're pretty close. And then you go on this side, Greek, Italian, Spanish, they are very close. So it's really hard to differentiate. It's basically the same picture, but a different presentation. So depends. Like I think that's most representative. Excuse me?
Filipino correlates with all of them.
Not really. No.
Isn't it?
Yeah, that's a good point. Yeah. Filipino and Jamaican. Yeah. Brazilian a little bit, but yeah, Filipino, it stands out.
Do you know how those correlations are calculated? Is that just like a
based on the ingredients, like based on basically this information. So they have a set of ingredients. Okay. They take two sets and they compare what is the like.
Like, so do you think I could convince you to use your mouse cursor to point at things on the screen so the video and the live stream get it?
Okay.
Yeah.
Okay. So the results of the competition were pretty interesting. And another interesting thing about this competition is that it's the second time when it's running. So the first time, I think, was about 3 years ago. And it was actual competition for money. And this time around, it was kernels only, basically meaning that you compete on a code. And you have to publish your code, I believe. At least we have the second place there. And so basically, it just finished 2 weeks ago. And, 3 weeks ago, right? 3 weeks ago. And as you can see, top 10 are very close to each other. So there is not much difference. And I think, as I said, I think it's like very close to the maximum that you can get in that competition. And the interesting thing about this leaderboard is that all of them use the same kind of approach. What people tried?
Do you know what is the metric here? Is this accuracy?
Yeah, just accuracy.
Okay, so you just submit the dish. There's no probabilities.
Yeah, the submission file is very simple. It's a ID of the recipe and the cuisine, like number and, I don't know, Brazilian, right? Number and Italian. So it's just accuracy.
Is there any motivation on like accuracy? Because I mean, it looks like maybe the test set is quite small because of how clustered some of those scores are. And I'd have thought, if you could look at like the top 3 probability or some other metric, you might be able to sort of differentiate some of those teams a little bit better. But with accuracy, it's quite crude, right? So I think what happened. Such clustering.
I think what happened is that you're talking about this.
Yeah. Like the scores are incredibly.
Yeah. So what happened is that somebody posted like the results that they have and the code that they used, and it was so good that nobody could really beat it. So it was pretty close to top. So you could, and there was like discussion on the forum saying like this competition is not interesting because the code is already there. So you can just take this code, post it, and you will be in top like 10, 20, 30. Like it's just a little bit of tuning that you could do, but not much.
And so the size of the test set then was like 1,000?
It's maybe 10, 25,000. It's dozens of thousands.
Okay,
it's a pretty big one.
Because you said you'd finish early, I just want to make a quick comment. Did any of these guys complain about tying and like coming 7th and 8th?
I'm sorry, about what?
I noticed that these scores are the same, and if it's accuracy, I can maybe believe that they got
Based
the
on
exact
time?
same result. Merrick and Markson.
5th, 6th, 7th, and 8th.
Yeah. Anything on the forums?
Well, the thing is that the only thing you could win would be swag. So, like, T-shirt. So nobody complained, really. Like that was more like just a playground. So people would.
Fourth would be a bigger deal. Yeah, fair enough.
As I said, like everybody used, at least at the top, everybody used the same approach, and we will be discussing what that approach was. But some people tried all kind of different things, and first thing I would try would be word embeddings, and looking at the distance. No, it didn't work. I mean, everything worked to the point, and the point was about like 80%. So nobody could go over 80% except for the solution that we will be discussing. XGBoost, word embeddings, neural networks, logistic regression, in all combinations, in ensemble, like it couldn't improve over 80%. But one thing actually worked. And it basically 3 lines of code. This is 3 lines of code, yeah. Yeah, that's the whole competition. And because people posted it like pretty early, then became not very interesting. But because I never used that approach, I was impressed. So this is actually the code of the second place, and he posted that kernel. That we will be discussing 3 things. Basically, what they did here is. They used one feature, just one feature, is TFIDF. And if you don't know what it is, it's like very simple. We'll discuss that next. And then they used support vector machine, but because of the algorithm of support vector machines, they work with one class only, basically 2 classes only. So they differentiate between 2 classes. And as we saw, we have like 17 of them. They had to use one versus rest classifier, which is, we also will see it's like very, very primitive. I'm sorry about that. I went there. I don't know. I used to teach for 9 years, and I was always kind of drawing something on a board, and it's hard for me to just stay in one place. I was teaching in Russian, so it was much easier for me. Anyway, so as I said, we will discuss all 3 lines of code, and the first one was TFIDF, which is term frequency inverse document frequency. That's something that is being used in many different places. It's like, for example, Google search would use it when they started, and SEO, and the search engine optimization, everybody's using it. What it's doing is basically takes the set of documents, and it takes terms in basically all the words, or bigrams, or trigrams, and counts the number of times it appears in all documents. And then it takes inverse document frequency, which is basically you calculate the weight of the term in terms of how often you can find it in documents. So you just, and the higher the weight, it means that fewer times you can find it in documents. So basically, when you have this weight very high, it means that the term occurs many times in a small number of documents. This is like a general description because for us, every term that would be ingredient, and every term happens only once in the document, right? In a recipe, you have only ingredient only once. But you can have some kind of ingredient that happens like only in small number of recipes. And that would make it very, very valuable. And the weight of TF-IDF will be very high because of that. And if you have something that happens like very often, for example, in our case, that would be salt or pepper. Basically, everybody uses it everywhere, and therefore that weight will be very low. So basically, and the way you can calculate this weight, there are many different ways. I just took one of the formulas that you can use, very simple one. There are more complicated ones, but the goal is the same. It's basically calculate the weight. And I'll just present one example using this formula. So let's say we have ginger root, and it's not very common. So let's say we have it about 1,000 times in our training set. And training set is 39,600. And you take a log. So just coming back here. Actually, in this competition, they used a different formula for TF. It's not just a raw number. It's not just 1,000. To make it more balanced, to take it more balanced, they take a log of it to make sure that you don't get 0 there. They have log 1 plus. So this is a first element, and IDF would be a log of the number of documents altogether, which is 39,600, and number of times you find that specific term. So, and as you see, for ginger root, we have pretty high weight, and for sugar that appears much more often in many recipes, we get this number like 2 times less or even more than that. So that's the single feature that was used in that competition. Just one feature, nothing else.
I'm a little bit confused here because what you're calculating there doesn't seem to match what you've got on the previous slide.
Yeah.
Oh, sorry. The way that I've understood it was that TF would be like a document-wise term, right? So you would only have, that would only count for the frequency that something occurs in a single document as opposed to
but in
how many
that
documents.
In that case, the first term will be always the same.
Yes, always
because
one.
Always, yeah. Yeah. So in my example, as I said, there are many ways to calculate it, and I just used one of them. So you can take that term frequency in a document, or you can take it in a subset of documents. So I took it like just as a whole, right? So, and still it makes sense, and still it works, right? So the goal is, as I said, if you open Wikipedia, you will see that there are so many ways to calculate this, and you can use any of them. The main goal is to give a weight. The higher weight means that you have term that is very significant, and the lower weight, something that is not. And we basically, even in that example, we get to this point.
Could you not just use the second term on its own then?
You could.
Okay.
Yeah, you could. But that's not something that is defined by that TF-IDF factorizer. I tried to use that specific example. So, and actually the the fact that I was using log here is also, this is like a main formula, but I use log here because of you see that sublinear TF equal to true. So it means that term frequency will be used, you will be using this formula, logarithm of 1 plus TF.
Just a quick note for in this case, it won't matter because like you either have the ingredient or you don't. But the way that this is often used in say like news articles or whatever. And if you have like a rare word that appears many times, then it should be weighted like much more.
Yeah.
So for example, like, I don't know, like strep or something like that, you would expect to be medicine, etc.
Yeah, so for Google search, like if you have a document on a specific topic and there is like very, very rare term that is being used in that document, and if you use it many, many times, Google will put that result higher just because that term appears like so many times. And this is like, it's having a big weight. It's rarely seen in all other documents that Google has, but for this specific document, it appears many times. So that's the goal of the, general formula, but we have like very specific case, and that's why it was modified to basically to do that.
Did anyone try to throw away specific ingredients that appeared like so many times to try and prove their accuracy? Did you see any cases of that, or
not in the code that I was looking at? So I still think like you don't want to really lose data. If it's like in every single document, maybe, but for example, even salt. When you look at these two. These two examples, it's on the top. It's not everywhere. Like if you open Chinese, it will be soy sauce. It won't be salt. So it's not like on every recipe. You don't want to lose that data.
So to me, what you just described sounds very Bayesian, right? So the probability of a cuisine given the presence of an ingredient is proportional to your probability of seeing this ingredient in that cuisine. So to me, you could just like use Bayes rule and build a classifier with that wouldn't require any training at all. And I wonder if anyone has done that.
I didn't get that part. What could you use?
So
Bayesian?
Yeah, so you could use Bayes rule.
Yeah, how Bayesian?
Yeah, so you could explain the probability of a cuisine given a list of ingredients as proportional to the probability of serving such ingredients in those cuisines. So that's very similar to what you just described. Like the probability of a certain cuisine is proportional to how many times you see that ingredient in that cuisine. So you could actually use that to write an actual probability distribution with no training at all. Just like you multiply those frequencies and it will give you a classifier. And I wonder if anyone did that. Yeah. It's pretty similar to what you explained, but this requires training and the other approach doesn't.
I think that people tried all different kind of things, and it seems like this one single metric, like it was able to crack this 80%. Like, because obviously you have all different kind of solutions. Like neural network would try to learn all these kind of things, and maybe it would put the weights on the ingredients as well, but nobody could crack that 80%, and only this specific feature was able to do that.
Well, just as an anecdote, I didn't know that this Kaggle was going to be about this competition, so I did this competition yesterday too. And I tried a neural net, and I could only get 0.79.
That's where everybody's stuck. Yeah, like just before 80%, everybody's stuck.
Yeah.
But when they were starting using this one, because it's not really like straightforward weight, it has this inverse document frequency in there, and I think that's what makes it different from just how often.
I think that tonight I'll try the Bayesian approach and see if that goes past the 80%, anyways.
Actually, I have a note on that. And my intuition is that Bayesian would not work if you are talking about naive Bayes, because the assumption that these ingredients are independent, actually, I think is not correct, because if it is Chinese cuisine, it is very likely that you will have soy sauce and other spice that is always in Chinese cuisine. So that assumption gets violated, but we can take this offline.
So, I mean, I may be jumping ahead because I don't know where you're going with this, but I feel really stupid right now. So I imagine these ingredients, like what we would normally do is we would take them and make like a one-hot encoded vector, right? So we have like 6,000 possible ingredients, and we're going to put a little one in the places where they existed and a zero otherwise. Are you proposing, like, you obviously, that we would compute weights and that it would be weights instead of ones? Is that what we mean by creating a feature from this?
Yeah. So basically, we'll get a matrix of the dimension will be the number of ingredients that we have, and it's about 12,000. So like 12,000 ingredients, most of them zeros, because they don't appear in the specific recipe. And obviously the number of rows would be in this matrix, the number of examples that you have. And like every single one of them will be zero except for like 5, 10, 15 that has this weight.
Right, and so in that sense, these weights, like especially since it's always a one, right? And I think the way they're calculating here, like the weight for ginger is always going to be the same weight. And so all of the values that used to be a 1 for ginger are going to become 4.79, right?
It won't be a one hot encoded.
Conceptually, it begins one hot encoded, right? Like we had ginger, right? And so you're saying the ginger element of the feature vector is not going to be 1, it's going to be 4.79. And in every recipe where ginger appears, it's going to be 4.79, right?
Absolutely. Right.
And so this entire column now in the matrix for ginger is going to be 0 or 4.79 and never any other value, right?
Yeah.
So that's interesting. So you haven't really added like any information, but you've set the support vector machine up to succeed or something, right? It's kind of like it's a learnability benefit or something, right?
So why do you think that it doesn't provide more information to SVM to solve this?
Well, there's still only 2 values. I mean, you've kind of scaled the space a little bit.
It's not 2
right?
values, you have many.
No, but for ginger, I mean, for the ginger entry, it's only ever 0 and 4.79, right? I mean, it's not much.
I'm sorry. So you have a ginger, let's say.
You're always doing 1 versus all of them. So for like an Asian cuisine, ginger is going to be very high. But if you're like asking, is this Italian? Ginger will have a very low value.
So I don't agree with that.
Or the other way around, but this is.
Yeah. So I actually, I'm not 100% sure, but I don't think that's how it works. But basically, because you have weights for, let's say, 10 ingredients for one recipe, like in combination, it makes a lot of difference because it's basically saying, look at this, look at that, and use that as with the bigger weight. So like this specific ingredient has a bigger weight then. And in combination, it makes sense because if you have ginger, let's say, and you have to choose between Chinese and Jamaican food, then they use both. But like, because it's the same weight, you kind of like, it doesn't make a decision based on that. It's saying like, well, I have 2 recipes to compare, like 10, and let's say I see these weights, and I know that ginger is not something that will solve this problem. So I will take something that has bigger weight for this specific classification, right? So I think that in combination, it actually makes sense.
This is an interesting conversation. I think the one part that's probably in your head and that was in my head is that if you have a model that's able to train learnable weights to go in front of all of these numbers, so in some sort of like linear regression or something like that, then a 4.79 with a machine weight of 0.25 in front of it is going to essentially capture the same amount as a weight of 1 with a number 1. So you're actually not adding any kind of like complexity to your end model. But I think that there is an argument for learnability and starting with a higher weight. Like if the model is just going to be like originally assigning weights randomly, then having important terms have a higher weight might incentivize the model to kind of treat those.
Well, again, that's the all the code that they use, right? This is the whole model. So do you see anything that tells you that there is additional kind of?
I may have had a revelation. If I have a recipe with 4 ingredients, one of which is ginger, or I have a recipe where I have 16 ingredients, one of which is ginger, does that change this value? I mean,
why not?
Oh yeah, that's that would make this much more interesting, wouldn't it? That's why I'm sort of realizing maybe that's the case. Okay.
But not based on this code,
No.
right?
Well, I don't know what's going on in those functions, so who knows?
No, it's just basically taking that TFIDF vectorizer, which is like scikit-learn provided the function. So it doesn't have like anything else in there.
So I think we can maybe continue this once we get into what the SVC actually does, because I'm not familiar with
let's talk about that, because I didn't expect too many questions here. It's very straightforward. So one versus rest classifier. This is like again very simple. It's a very simple approach that you can use. Because that algorithm that we'll be discussing next, SVM, it's always deciding between 2 classes and basically deciding which class you are looking at. You have to transform your data set to the 2 classes, and one of the ways to do that is to use one versus all or one versus rest approach. And what we do to train the data, we take one class and we compare it to all others, and we say, like, let's say class 1 is a positive example and all others are negative examples, and we will compare them. And then we'll take the second class and we'll say this is positive example now and all others are negative. So and this approach allows us to use SVM. And again, it actually could be done right here in that line, so where the decision function shape defined. So this line is not actually needed. It could be done inside the SVM itself, and it would use this one versus rest, but for whatever reason, they decided to take it outside of this function. Okay, so let's talk about support vector machines. That's something that was really interesting and something that I never used. It's a very simple concept, and this is something that it's been around for 25 years now. And one interesting fun fact is that the guy who invented that, he's actually coming from my home country, Uzbekistan. And he invented that in 1960s while still in USSR. And then nobody used that until he moved to US at the age of 60, I think, at 91. He moved to USSR. He published that work that he did like 30 years ago, and it took off. And it's like, he works, he's 80 years old now, and he works for Facebook research. Yeah. So, but he's still around, and this algorithm proves that, like, it's pretty useful up until now, although we have all other new shiny things like neural networks. Anyway, the algorithm itself is just, it gives you a way to distinguish between two classes, and it searches for optimal hyperplane, which maximizes the distance between two classes, and minimizing the risk of misclassifying the training samples, which is basically the same. So the main goal is to maximize the distance between two classes and find that frontier that is doing that. So the definition is not very clear, and if you actually watch most of the description videos and like lectures, it's like really hard to understand, but the concept is very simple. It's like very straightforward. So let's take a look at the example. Let's say we have two classes and we want to differentiate them. We have male and females, and we want to differentiate them based on height and weight. And we have some data points here. Let's assume that this is true. And our goal is to find that line that would cross these two classes, and it would be the best describing the difference between them. And we have many choices to do that, obviously, like we can put many different lines in there, but the best one would be probably line number 1. And why? It's just based on that definition that we have, because it's maximizing the distance from closest points. So let's say, I don't think you really can see it. Well, anyway, so let's say we have this man here, this data point, this woman here. So it will be somewhere in between, obviously, right? But where? And the way to find out that, we need to find this maximum space and this hyperplane, or this line that separates them. So we take those 2 points and we find support vectors. Support vectors, that would be data points that we want to use as a way to calculate basically that distance. So we take closest points, and based on that, we find that line. There is lots of math in there. You can find that, and there is a good MIT lecture where the guy goes through the whole theory. Like it takes 40 minutes to describe how to calculate this distance. But basically, what we need to find is margin, so the distance between two closest points, and it will be perpendicular to that d minus d plus. So this is a distance between negative examples and distance between positive examples, and the line will be right in between. So, and we call that hyperplane. So when you look at that picture, it kind of makes sense. Well, again, if you want to find out what the math is behind that, you can find lots of information online. But if you look at that code that we use for machine learning, you don't really need to know the math. You basically provide that couple of parameters there, and most of these parameters have a default value. We will talk about 2 or 3 that you can use to tune that model. But basically, you just say like, okay, I have 2 classes. I need to find this hyperplane, and it will do that for you. Again, there are lots of formulas, but we don't really care. But what you need to understand is that when we find that line, it works pretty well in this specific example, and it works because that's something that we can visualize. So we could draw that line by ourselves. We don't need that algorithm. The problem here is that we have only 2 features that we are looking at. But what if you have 3, 5, 10,000 features, and you need to be able to differentiate classes based on that many features? The way it's done there, it's very, very interesting. It's called Kernel Trick. So what it's doing, it's basically transforming your data set to a higher dimension. It's very easy to understand on this transition between one-dimensional space to two-dimensional space. So let's say you have this data set, which is, I don't know, like let's say just weight. And based on weight, you try to say, what's that?
A health risk.
No, well, let's say health risk. I don't know, like, but that would be like just something that that you want to differentiate. But because you have classes that are not really sequential, so you have like one class in the middle and two classes on the other side, it's hard to do that in one-dimensional space. But when you apply some kind of logic to that, let's say you just take the simple function like x squared, and by applying this function, you basically introducing new feature. You had just one feature, now you have two features. And this feature y is basically giving you an option, transforming that to two-dimensional space. And in this space, you can easily differentiate those two and put that line hyperplane in there. So why it's called hyperplane? Because when you go in higher dimensions, it will be the same behavior, but it will be like a plane, right? So here is that example. When you go from two-dimensional space to three-dimensional space, let's say you have a data set that is kind of like have a circle in the middle, and you need to find that, like you cannot draw the line here. There is no way you can use some kind of linear function to differentiate between those two classes. But as soon as you get to that additional dimension, it becomes very easy. And in this case, you can use some kind of function that, again, will, I think x squared would work as well, maybe here. Yeah, I think it will. Anyway, there are many different functions, and they called kernel functions that you can use. And the interesting thing that when you use those kernel functions, we have several types of them. And again, there is like a math behind it, but you don't really need to understand that, because what most people do, they start with very simple linear, which is here, which you can see here or here. So the linear approach would work in many cases. But if you have some kind of like tricky, tricky classes that has non-linear differentiation, then you could use polynomial. You could use sigmoid, or what is being used in that computation, and it's actually default for support vector classifier in Python. It's a radial basis function, RBF, and it's using this exponent and a couple of parameters that you can provide. This parameter gamma is like the biggest thing that you need to work on. And there is also a cost that you can apply, basically, for your loss function. You can define a cost. And we will see that on the next slide. It's just I want to point out that on that graph, you can see how linear is differentiated from RBF. So it's basically has this additional curve in it. And obviously, sigmoid and polynomial provide you the same kind of approach that you can use. So, and the best thing that, although it actually takes you to the higher dimensional spaces, you still work with the matrices. You're basically multiplying matrices there, and there is not like, something that requires lots of calculation. Although the number of calculations that you need to apply depends on the number of the features that you use. And in our case, we have like 1,200 features, which is like a lot. Basically, you go like to the I don't know, like 1,000-dimensional space by using these features. So, but it still works, and it's using the same approach, and there are just a couple parameters you need to use. So first of all, you need to decide which kernel type you will be using. That's one thing. And again, if you have like really simple data set, try linear because it will be faster. And if not, then try RBF, and in most cases it will be fine. And this is just a fine tuning. Like to run this data set, I actually started when we...
Can I ask a question?
Yeah, well, it's still running, but it's been like less than an hour. It will be finished like, I don't know, like in 20 minutes. So this is using 1,200 features and using RBF. And again, like I just took this code and it works. And we will see the predictions if it's finished sometime. So, yeah.
So those figures that you were showing, they had 3 colors. So I assume those are 3 classes. And so what you show is the result of using more than one hyperplanes, and like then you put them together somehow. Like the hyperplanes usually are binary, right?
I'm sorry.
So the way I understood from what you explained, those hyperplanes, they usually give you a binary output, like they choose between 2 classes.
Yeah.
And here in these figures, we see 3 classes, I assume. So this is the combination of 3 different hyperplanes.
I think that's the result after you actually do the one versus rest, because as you could see in that scikit-learn function, you could actually provide this the one versus rest like specifically there. So it's more like SVC example. Basically, this is something that I took from a working Python code. There is a link there. You can go there, and so they had 3 classes.
Mm-hmm.
But internally, like you don't have to think about it. That's the best thing about this whole thing, that it's basically one line. So there is a preparation of data that you need to do, but after you provide the data, it's just do everything for you. It's just do that multi-class classification by comparing one class to all others, and then in the end you actually get like the model that works with many classes, but internally it's using that one versus all.
Okay.
So, and this, yeah.
Okay, I was also thinking kernel can also go the other way from higher dimension to lower dimensions too. So I think that's one way they handle the cost of dimensionality in SVMs.
That's a good point. So it's not really, by using the kernel, you're introducing a new feature, but it's not taking you to the higher dimensional space. It's just basically you just calculate one more thing, right? So that's the kernel function, what it's doing. So, but you can think about it as additional feature, right? So it's just a way to understand it, like what is happening there? How does it differentiate?
I have one more question about other methods that were failing. Did you investigate to see where it was failing? Like Like you want to see what kind of cases does those other models, like the neural networks, where do they fail and where does this pass? So like, did you identify any samples of where those kind of failure points are? It's like debugging the competition.
So I think what everybody did, I haven't used the validation set there. So there was just training and test. So, and honestly, when you ask that, I kind of realized that I haven't seen anybody doing that. So it seems like everybody was using the test set and posting it to leaderboard as a kind of like a validation. But that would be interesting to see. But I'm pretty sure that just based on the type of data I was looking at, sometimes you just cannot tell. It's just not enough information to decide. So there is not much debugging or troubleshooting you can do. I'm pretty sure that people did. Some people did, but that's not helpful. I don't think so. Well, anyway, as I said, there are some formulas, but you don't need to know them. What you need to do is to see that in different types of functions, you need to tune different parameters. For example, if you use polynomial, you can tune D and R. In our case, because we're using RBF, you just tune gamma. And that's the behavior you can get with changing this gamma. So basically, the higher the gamma, basically the closer it tries to find that function that will fit the data, but obviously that could lead to overfitting. And there is also penalty, which kind of like a cost, and it shows you how smooth you should be like in terms of defining these boundaries for this decision function or decision boundaries. And so do you have any other questions? Because that's basically close to the end. And SVMs, they have some pros and cons, and the best thing about them is just how easy it is to implement these things. So if you have a task of classification and you have a limited number of features, it works amazingly well. And it's very effective in high dimensional spaces, as we saw. And it also has an interesting property that it guarantees to find global minimum. It will not start at the local minimum somewhere. And the cons are is that it's not very efficient with very large data, and very large, that could be like, when you have millions and millions of examples and maybe thousands of features, it won't work really well. I mean, it could find that that model, but it will take just forever. And it's obviously not very good when target classes are overlapping. So you have lots of data points that are close to each other, because it basically tries to, or even if they are like, if there are lots of outliers, it doesn't do the good job. And another problem with that is that SVM, they don't provide probability estimates unless you use, there is a parameter there, I think it was there, and this, there is a cross-validation that you can do, but it will take lots of time. So the probability is equal to false. It's right here in the middle. So we don't ask for probability estimates. If you put that to true, it will take just much, much longer. And that's maybe the reason why, yeah?
While we're here. Actually, sorry, can you navigate to the drawing the line between men and women?
Yeah.
So I think I have an answer to my question. And forgive me if it takes a little bit of time and if I don't communicate it well. So I mean, based on this diagram, I think this captures nicely that that these SVMs are quite. They should be sensitive. Oh no. Did I back out? I think I'll bring it on. It's dead. Oh, well, I turned it back on, but we'll see. Nope. Oh, well, we'll see how long that lasts. So it should be sensitive to like the scaling of your features, right? Because it's trying to create this maximum distance. And so if you thought about this chart, like the way we chose those axes really set up like how much emphasis I put on height versus weight when I calculate that distance. And if I stretch this way out to the right for weight, then weight would become kind of more important for drawing these hyperplanes. And so I think that's now what we did with the weights was we put more emphasis on certain features in the SVM for drawing those hyperplanes. And so we didn't really add information exactly, but we sort of prioritized things for the learning.
Yeah, that's what I was trying to communicate, that when you have so many features, like when you have several ingredients and every one of them have a weight, in this many dimensional space, it will move it somewhere, right, to the different kind of like point. And it will be able to differentiate between this point and that point just because some of the weights are kind of like pushing it to the other direction.
Just want to make a comment. I'm still like I still have a concern about your question. I think that I mean, if you call it kernel trick, is not necessarily help us. It, like the question that you like initiate, I think still, at least for me, is not responded. So basically, the structure of the data in your spaces matters, but like not necessarily that function helps. That's what I'm like.
Right. Okay, actually, this is great. Can we go to a few slides before where you say what doesn't work, what's not cooking? I believe is this slide.
Yeah. Everything else.
So I think maybe let's go through some of these and describe why this trick does not work in these situations, right? So in a random forest or in an XGBoost, decision trees are always, they don't care about the scale of your variables. They're only going to kind of pick a midpoint between the two values and say if it's above this, then it does this thing, and if it's below this, then it does this other thing. So XGBoost doesn't care at all about this information that you're putting in. Logistic regression, this is a model which is going to essentially train a weight for each of these values that it thinks is important. So in the end of the day, this one also doesn't care about what those values are, especially if there's only two, if it's a 0 or if it's a 1 or if it's a 0 or it's a 2, it doesn't care because it's just going to put a weight in front of it.
You can keep on going, I think you're wrong there.
Yeah. Oh, I'm well, let's get it out now because my argument for neural networks is almost the exact same. It's the trainable weights and word embeddings.
I think what's actually happened here is that there's not a ton of like test data, and SVMs just happen to do like slightly better. So what I think is happening here, why they actually have the TFIDF, is because SVMs, like logistic regression, have like regularization strengths, right? And it's kind of built into the kernel itself. So if we have that, then we want to make sure that. So for regularization, essentially has like a penalty for upweighting things by a lot. So if you're saying that, say, salt is very, very important to Cajun cuisine, that means that you're going to have to pay a penalty for a bunch of other things. So it'll find a different optimum, and it'll probably say, oh, actually, like Cajun spice or whatever is in Cajun food, like is more important, and it's going to give a more efficient weighting to those very special things that are only in one cuisine versus another.
Okay. I don't agree completely. As soon as you start throwing regularization in there, though, then all of a sudden the weights aren't all treated equally. So if you have a weight that's very, very low, but the model wants to weight it higher, then it's going to not be allowed to do it if you're adding regularization. So in some ways, logistic regression would also use these weights. Once you regularize it. what else did you say? Yeah, but the support vector machines, by putting this information in, and you definitely are adding information about how important kind of certain features are, you're forcing it to use this information more strongly than you're forcing these other ones to do. So you're kind of constraining and regularizing your model more. And under certain conditions, maybe in this case, data was just so noisy that any of these more powerful models would just overfit to it and not be able to do well in a test set. I think that might be the ultimate reason why it did well in this case, is because we don't have enough testing data to really get it to, or yeah, we don't have enough information in the data set to really kind of do well with these more complicated models that have all these weights. So that the support vector machine, while it's simpler, does better under these conditions. Yeah?
Sorry, I didn't look at the competition data, but, and I think just based on my understanding, do we know for sure that there's no sort of duplicate words in the ingredients, like for example, like green peppers and red peppers, that could change the term frequency for the TFIDF? Because I don't know if you looked at the, how did you calculate actually make sure like all the weights are the same for the entire row? Because there could be like one record where like, you know, it's both red peppers and green peppers, so the TF value is different when it does the multiplication. Something just look into. That's sort of my thought when I was reading up on it. But when you do the calculation, you assume that, I'm assuming you split all the words up, right? And you look at peppers twice.
But you would want to do it like this.
You'd want to do it like that, but I don't know how the sklearn implements it though.
Well,
So there's separator tokens.
So we're actually running out of time, so we'll try to wrap this up in just maybe 2 more comments. You'll have a comment and somebody can argue.
No, okay, well.
My comment is that you can always separate all words. So pepper will be a word and green will be another word and red will be another word. And if it doesn't really matter if it's green or red, then green or red will have a 0 weight at the end. Yeah, I don't know.
Yeah, well,
I mean, actually, let me have the last word because ideally you would want to implement your own tokenizer so that each thing was taken completely separately and counted on its own. That's probably what they did here. Okay, so we're going to wrap things up. I just have a couple words before we kind of go take the long trek to go get dinner. Hopefully a few people were convinced by Bruce's spiel at the beginning. I would like to second that and second what Alexei said at the start of his talk. It is a really great experience kind of doing one of these talks, and it really kind of puts you out there, especially if you're looking for work. We've had a history of placing people that have done presentations. So if you're looking for work, you don't have anything to do, and you want to learn about a competition, you want to really get into machine learning, we're a very welcoming group. Bruce and I will both help you with the presentation and point you in a good direction. You'll get some great practice public speaking. I mean, it's really like win. So hopefully, yeah, if that's interesting to you, just message Bruce or myself on Slack. And regardless of what happens, we'll make something work for 2 weeks from now today. So I'll see everybody here in 2 weeks. Finally, oh, yes, yeah. Big round of applause for Alexei. He didn't mention this, but he was great. He only had a week to prepare for this because Bruce and I came to him in a panicked state saying that we needed a presenter, and he stepped up. So really, yeah, thank you so much. It was great, especially on short notice. So anybody that wants to come get drinks, just hang out here for 5 minutes. We'll put the tables away, and then we'll all walk down together. Thank you, everybody.
So by the way, it's finished, right? It took like exactly one presentation.
Yeah.